Integration of metabolism. In this slide presentation, we will review the interrelationship between carbohydrate, protein, and lipid metabolism. We will discuss the central role of the liver in this integration of metabolism, as well as the macronutrient interconversions. Here in this diagram, we will see the metabolism of protein, carbohydrate, and fat. We see with their metabolism the interrelationships between each and key intermediates such as pyruvate and acetyl-CoA. We also see that each of the macronutrients undergo the process of the Krebs cycle when they're oxidized, and from there they undergo the electron transport chain for ATP synthesis. You can take a moment to further review this diagram and the interrelationship between protein, carbohydrate, and fat metabolism. As mentioned, we see that these macronutrients share pathways of energy metabolism, with pyruvate and acetyl-CoA being central intermediates. We see interrelationships between pathways. For example, we've seen that the carbon dioxide produced from the Krebs cycle is used in fatty acid synthesis, also in gluconeogenesis. The citrate formed from the Krebs cycle is used in fatty acid synthesis. We also see that oxaloacetate and alpha-ketoglutarate additionally link carbohydrate, lipid, and fat metabolism. These integrative pathways are also involving substrate used for either tissue storage or catabolic processes. So we can see these different processes, and they can either be categorized as tissue storage processes or catabolic processes. We see glycogenolysis, glycogenesis, gluconeogenesis, fatty acid oxidation, and fatty acid synthesis, with the tissue storage processes being glycogenesis and fatty acid synthesis, and the catabolic processes being glycogenolysis, fatty acid oxidation, and gluconeogenesis being a conversion process from a non-carbohydrate substrate to glucose in instances of fasting or starvation. We see that the liver plays a key role in the metabolic pathways for each of the macronutrients. It acts as a processor and distributor. For carbohydrate metabolism, it's involved in glycogenesis and glycogenolysis, additionally in gluconeogenesis. For protein metabolism, it's involved in synthesizing proteins, catabolizing proteins, and converting proteins to other compounds. For fat and lipid metabolism, it's involved in lipoprotein synthesis and cholesterol synthesis. In addition, it's involved in fatty acid synthesis and beta oxidation. We also see that the ketone bodies are formed in the liver. We have three diagrams that will depict the role of the liver in carbohydrate metabolism, protein and amino acid metabolism, and lipid metabolism. In each of the diagrams, we're going to see arrows either pointing up or down or from side to side. We can see that arrows pointing side to side are reactions that are indicating distributing products from one tissue to another. Arrows of catabolic pathways are pointing downwards, whereas arrows of anabolic pathways or reactions are pointing upwards. Therefore, this diagram depicts processes of carbohydrate metabolism and the key central role of the liver. Key to the processes of carbohydrate metabolism is the intermediate glucose 6-phosphate. We can see here that there are several fates of glucose 6-phosphate. So we can see here that glucose 6-phosphate can be converted to glucose 1-phosphate and then be stored as liver glycogen. We can also see that glucose 6-phosphate can be dephosphorylated, leaving the liver and entering circulation to supply blood glucose. We can see that glucose 6-phosphate can undergo the pathway of the pentose phosphate pathway, forming NADPH and ribose 5-phosphate. We can also see that glucose 6-phosphate can undergo the reaction and processes of glycolysis and form pyruvate. So those would be the four potential fates of this key intermediate glucose 6-phosphate, either undergoing glycogenesis, being dephosphorylated and entering circulation to supply blood glucose, undergoing the pentose phosphate pathway, or undergoing glycolysis to form pyruvate. And then we see key to carbohydrate metabolism is the conversion of pyruvate to acetyl-CoA. And then we have acetyl-CoA having two potential fates, either being involved in these anabolic tissue storage processes. We see cholesterol synthesis, fatty acid synthesis, formation of triacylglycerols, or we have the catabolic processes of the oxidation of acetyl-CoA and the formation of ATP through the electron transport chain. Next, we have amino acid and protein metabolism, and we see the central role of the liver here as well. Here in this diagram, we will see the potential fates of the amino acids in the liver. So first, we can see that they can be used to form body proteins or other related compounds. So we see either proteins of the liver, plasma proteins, or tissue proteins, or we see its involvement in formation of nucleotides, hormones, and porphyrins. In addition to being involved in the formation of body proteins, we also see that the amino acids from the liver can be deaminated. We see removal of the nitrogen group in the form of ammonia, and that ammonia will then need to be converted to urea in the urea cycle. When deaminated, amino acids will become one of several alpha-keto acids. However, a key alpha-keto acid would be pyruvate. And we see eventual fates of pyruvate, one being the process of gluconeogenesis, so we see conversion to glucose in the liver, and then that glucose can be transported to the muscle and used to fuel the muscle. We also see here depicted the alanine glucose cycle, so alanine coming from the muscle being converted to pyruvate, then being converted to glucose, which would then, that glucose from the glucose alanine cycle will then go to fuel the muscle. Additional fates of pyruvate would be conversion to acetyl-CoA, and then acetyl-CoA can undergo the anabolic process of fatty acid synthesis, or can be oxidized through the Krebs cycle and the electron transport chain to make ATP. Next, we see the metabolism of lipids and the central role of the liver in these processes as well. We can see that these fatty acids can be packaged into triacylglycerol molecules to supply lipids of the liver. We can see it can be packaged into triacylglycerol molecules to store lipid in adipose tissue. Additionally, we can see that the fatty acids can be transported out into circulation to supply the free fatty acids in the blood, or we can see that the fatty acids can be used to form lipoproteins, which would then exit the liver and be circulating as plasma lipoproteins. So we see these four potential paths. So the triacylglycerol molecules of the liver, triacylglycerols to be stored in adipose tissue. We see formation of the lipoproteins to be transported through the plasma. And then also we see the free fatty acids that would leave the liver and be transported through circulation. The fatty acids can also undergo catabolic processes, so they can be oxidized through the process of beta oxidation. And with beta oxidation, we have a formation of an NADH and an FADH2, and then an acetyl-CoA. So that's each cycle of beta oxidation, we make NADH, FADH2, and an acetyl-CoA. And the acetyl-CoA in lipid metabolism can undergo different fates. So the acetyl-CoA can be used to form the ketone bodies in the blood, and this would be particularly under starvation conditions or with a very low carbohydrate diet. Acetyl-CoA can undergo anabolic processes in forming cholesterol and also steroid hormones. Additionally, we can see that acetyl-CoA can be oxidized through the Krebs cycle, and then the intermediates of the Krebs cycle then can be used to power the electron transport chain and ATP synthesis. Lastly, in this first slide presentation on the integration of metabolism, we will discuss the macronutrient interconversions. So we see the macronutrient interconversions for carbohydrate intermediates, protein intermediates, and lipid intermediates. First, we will discuss carbohydrate intermediates. We can see that carbohydrate intermediates, particularly glucose, can easily be converted to fatty acids, and this is through the conversion of glucose to pyruvate in the process of glycolysis, and then in the pyruvate dehydrogenase complex we have conversion of pyruvate to acetyl-CoA. We know from previous slide presentations that acetyl-CoA, under the correct metabolic environment, can undergo the process of fatty acid synthesis. Of course, acetyl-CoA would need to be converted to malonyl-CoA, but it does act as a substrate of fatty acid synthesis. To form triacylglycerols, the glucose can also be used as a precursor to the glycerol backbone, so glucose can form both glycerol, and glucose can form acetyl-CoA, which can then be converted to malonyl-CoA, and then a fatty acid. So carbohydrates, again, can easily be converted to fatty acids and triacylglycerols, and this would particularly be in a condition of a positive energy balance, so over a chronic period of time, a higher intake of calories compared to one's daily energy expenditure. Now we look at the protein intermediates and their conversion products. So we saw previously that when deaminated to each corresponding alpha keto acid, that most amino acids are glucogenic. So all amino acids except for leucine and lysine can be converted to substrates that can undergo gluconeogenesis and therefore be converted to glucose. Additionally, amino acids, when deaminated, can also be converted to fat. So when the glucogenic amino acids are converted to glucose, the glucose can undergo glycolysis, be converted to pyruvate, and then from pyruvate it can undergo the pyruvate dehydrogenase complex and be converted to acetyl-CoA. And we mentioned previously that acetyl-CoA, when converted to malonyl-CoA, is going to be the substrate of fatty acid synthesis. Also, the glucose that can be formed from glucogenic amino acids can be used to form the glycerol backbone of triacylglycerol. So we see here as a summary of the amino acid macronutrient interconversions that primarily when the amino acids are deaminated to its corresponding alpha keto acid, it can be used to be oxidized to produce ATP, but it can also be undergo gluconeogenesis to form glucose. It can also form ketone bodies for those amino acids that are ketogenic, and the carbon skeleton can also be converted to pyruvate and acetyl-CoA and then undergo fatty acid synthesis. We will now discuss the lipid intermediate interconversions. Lipid intermediates are not as fluid as intermediates of carbohydrate and protein metabolism. Fat as a whole, when catabolized to acetyl-CoA, cannot be converted to glucose. This is because the pyruvate dehydrogenase complex is irreversible. So pyruvate can be converted to acetyl-CoA, but acetyl-CoA cannot be converted to pyruvate. Therefore, the acetyl-CoA cannot undergo gluconeogenesis. So largely we see that fat cannot be converted to glucose or other carbohydrate intermediates. There is one exception with the propionyl-CoA intermediate of lipid metabolism. We learned previously that propionyl-CoA is formed in the oxidation of odd-numbered fatty acid chains. So we saw previously that the propionyl-CoA can be converted to succinyl-CoA, and the succinyl-CoA can undergo gluconeogenesis. So propionyl-CoA would be an exception where we see conversion of a lipid intermediate to glucose.